Good day everyone. So for today's video, we're going to prove the structure of cyclic group and its theorem together with my pair. So first we have theorem 1. So if G is an infinite cyclic group generated by A, then every element of G aside from the identity has infinite order. To prove theorem 1, think of an infinite straight road or a stair. So every step you take, like a squared, a cube, takes you to a brand new spot. So you never look back and you never reach the end. So this means you never return your starting point, which is the identity. First, let's assume the opposite. Suppose an element x has infinite order n. So this means x to the power of n equals the identity e. Since a is the generator, we can write x as a to the power of key. So a to the power of key and n is equal to a over key n is equal to e. But in a finite group, the only way a to any power equals e is if the power is 0 or a to the power of 0. So this means that kn is equal to 0 since we pick an element that is not the identity or k is not equal to 0. Then n must be 0. So this contradicts our idea that the order was finite. So the order must be infinite.
So now let's proceed to the theorem number 2. Let G be a cyclic group of infinite order. If A is an element of G and A is not the identity, then for all U, V is an element of integers, A raised to the power of U is equals to A raised to the power of V if and only if U is equals to E. To prove this, theorem number 2, we suppose that, back to our straight road, if two people say that they are at the same mile marker, it means they took the exact same number of steps. There is no other way to land on the same spot on a line that never curves. To prove this, we look at A raised to the power of U is equals to A raised to the power of V. If we move everything to one side, we get A raised to the power of U minus V is equals to E. Based on theorem number 1, we know that in an infinite group, the power only equals E if the exponent is 0. Therefore, U minus V must be 0. If you add V to both sides, you get U is equals to V. This proves they must be the same.
Now let's proceed to theorem 3. Let G be a cyclic group of finite order if A any element of G such that absolute value of A is equal to n, then for all U, V, any element of integers such AU is equal to A to the power of B, F and only if n divide U minus V. Now, think of a clock. If the clock has 12 hours, which is n is equal to 12, and I move 1 hour or 13 hours, which is a to the power of 13, I land on the same number. Why? Because the difference is 12 minus 1 full circle. So they match because the difference is a multiple of the clock size.
To prove this theorem number 3, if n divides the difference, the quantity of u minus v, then u minus v is equals to nq. This means a raised to the power of u is equals to a raised to the power of v multiplied by the quantity of a raised to the power of n quantity raised to the power of q. Since a raised to the power of n is the identity, then a raised to the power of u just equals to a raised to the power of v. Now, what if a raised to the power of u is equals to a raised to the power of v? That means a raised to the power of u minus v is equals to e. If we divide u minus v by n, we might have a remainder r. So, a raised to r is equals to e. But n is the smallest positive number that gets us to the identity. Since r is the smaller than n, the only way a raised to the power of r can be e is if r is 0. This proves n must divide the difference perfectly.
To conclude everything, so we've seen that the structure of a cyclic group depends on its size. So if the group is infinite, it's like a straight line. Every power is a new destination and you never come back to where you started. So that is why a to the power of u only equals a to the power of b if u and v are exactly the same number.
But if the group is finite, it's like a circle or a clock. You eventually loop back to the identity. So in this case, a raised to the power of u and a raised to the power of v land on the same spot as long as the difference between them is a full trip around the circle. Or mathematically, if n divides u minus v. Understanding these three theorems help us see the skeleton of cyclic groups and how they behave in both algebra and real-world cycles. Thank you for watching, and I hope this made the structure of cyclic groups much easier to understand. Thank you!